In the previous class, what we have seen is that there exists something called the surface resistance to radiation, which connects between the radiative potential of the surface had this been a black body and the radiosity of the surface, which is the radiative flux just which is can be observed just outside of the surface. Based on these concepts, we are going to start our first network method for a very simple case, which is a two zone enclosure. So, you have two surfaces which are forming an enclosure, and we would like to find out what is the net heat exchange between these two surfaces which are forming the enclosure. So, let us look at how this would look like. So, it is a two zone enclosure, and this is my zone 1, where the area is A I, it is at a temperature of T A 1, temperature is at T 1, and the value of epsilon is epsilon 1. The rest is zone 2, which again has area A 2, the temperature T 2, and the emissivity is epsilon 2. So, zone 1 and 2 are maintained at constant temperatures. And we would like to find out what is the net radiative heat exchange between the two. So, let us call the net radiative heat exchange between 1 and 2 as Q 1 2, which is the net radiation heat transfer from 1 zone 1 to 2. So, the amount of heat transfer from 1 to 2 is called as Q 1 2. So, if I make an energy balance, so from an energy balance, I can write that Q 1 to 2 is the algebraic sum of radiation energy which is leaving A 1 that strikes A 2 this is one which is leaving this one minus the radiation energy leaving A 2 that strikes this must be the amount of net radiation heat transfer from 1 to 2. So, some amount of radiative energy is coming out of A 1 and it is going to strike A 2. So, it is the radiative energy which is leaving A 1 that strikes A 2, and the other one is this is also the 2 is also emitting energy, and a fraction of that energy may strike zone 1. So, Q 1 2, which is the net radiative heat transfer from 1 to 2, must be equal to this. So, let us try to fill up try to express this in terms of known quantities. So, what is the radiation energy leaving A 1? This is the radiosity, because radiosity is the potential of zone 1 which is seen by an observer who is standing just outside of A 1. So, therefore, the surface 1 has potential with the radiation energy which is coming out of surface 1 must be equal to J 1. Now, a fraction of that is going to strike the second surface. So, what is the fraction of that surface? It is going to be A 1 F 1 to 2, that is the view factor. So, A 1 F 1 to 2 multiplied by J1 would give you the radiation energy leaving A1 that strikes A2. Similarly, the radiation energy leaving A2 is J2, and what the a fraction of that is going to strike surface 1. So, this must be equal to A2 F2 to 1. I will go through it once again. This is the net radiation heat transfer from 1 to 2. So, 1 to 2 must be equal to whatever be the radiation energy leaving A1 that strikes A2. The radiation energy which is leaving A1 is this, which is watt per meter square times meter square. So, this is the total radiation energy which is leaving surface 1. A fraction of that is going to strike 2. What would that fraction be? From the definition of view factor, we know that F12, which is from 1 to 2, would give us the amount of the fraction of energy emitted by 1 that strikes 2. So, the amount of energy is J1 A1. So, the fraction that strikes 2 is J1 A1 times F12. Similarly, the radiation energy which is leaving A2 is J2 multiplied by A2. So, of this amount of energy, this fraction is going to strike 1. So, the radiative energy leaving A2 that strikes A1 would simply be J2 A2 times F2 to 1. So, we can then take it a little bit further to be as A1 F1 to 2 times J1 minus J2, and we are simply used the reciprocity relation that A1 F1 to 2 should be equal to A2 F2 to 1. So, using the reciprocity relation, I can express it in this way. So, therefore, this is Q1 to 2 is simply equal to J1 minus J2 by 1 by F A1 F1 to 2. So, this A1 F1 to 2 is nothing but the resistance which is 1 by A1 F1 to 2. So, J1 and J2 are the radiosities of surface 1 and surface 2. These two are the potentials, and from the fundamental equation we can see that these two potentials are to be divided by 1 by A1 F12 to obtain what is the net heat flow from 1 to 2. So, if this is the current, this is the potential difference, then this denominator must be equal to some sort of a resistance which is defined as 1 by A1 F12, and this is the resistance between 1 and 2 is R1 to 2. So, when we think of the surface, when we think of this surface once again, this is my 1 and this is my 2, in between I have R1 to 2, the potential at this point is J1, the potential at this point is J2, and if I have assumed these to be black bodies with potentials at EB1 and EB2, then the resistance in between these two is what we have defined before. So, if this is R1 and this is R2, then I can write this, draw this circuit diagram as EB1, this is my J1, this is my J2 and this is EB2. They are connected by a resistance which is the surface resistance to radiation for surface 1. This is R2, which is the surface resistance to radiation for surface 2, and in between I have R1 2 with, and we already know what is R1 and what is R2. So, I can write this as EB1 minus EB2, these are the potential difference. So, the heat flow from 1 to 2 must be equal to the potential difference by the sum of these three resistances which are in series. So, R1 plus R1 to 2 plus R2. And when you substitute the form for this is going to be sigma T1 to the power 4, these are black body potentials, minus sigma T2 to the power 4, and when you plug in the expression for R1, it is as we have done in the last class 1 minus epsilon 1 by A on epsilon 1, plus for the case of R12, as we have seen in this case R1 to 2 is simply A1 F12. So, this is going to be 1 by A1 F1 to 2, plus for the case of R2 it is going to be 1 minus epsilon 2 by A2 epsilon 2. So, this gives you the amount of heat which is to be which is to be supplied from this is the from Q1 to 2, which is Q1 to Q2. This concept, this is for the relation for a 2 zone enclosure. The concept of 2 zone enclosure, which is straightforward, can now be extended for more realistic situations like 3 zone enclosure. So, what is a 3 zone enclosure and how do I express it in terms of the concepts that we have developed so far? So, instead of 2 surfaces as was done previously, now I have 3 surfaces. So, previously one surface was interacting with only one other surface. In this case, one surface for a 3 zone enclosure, one surface would be interacting with two more surfaces. So, there will be 3 radiosities to deal with J1, J2 and J3. 3 black body radiation power is to be considered, which is EB1, EB2, EB3. EB1 and J1 are connected, EB2 and J2 are connected, EB3 and J3 are connected by the relation 1 minus epsilon I by AI epsilon I. That is the resistance in between. But what happens in between? Let us quickly take a look at it and then we will be in a position to do all these furnace calculations and so on. So, our next topic which we are going to consider now is how to formulate the circuit diagram for a 3 zone enclosure. Okay, the enclosure is being formed by 3 zones. So, let us see what 3 zone enclosure look like. And in 3 zone enclosure, the Q I to J, the heat flow from I to J would be J I, radiosity of I minus radiosity of J divided by R of I to J, okay, where we understand that R of I to J would be 1 by A I F I to J, which due to reciprocity would be equal to A j F j to I. So, this is the background one which we need to find out. So, this is exchange between 1 and 2, and for Q I, which should be equal to E b I minus J I by R I, where R I would simply be 1 minus epsilon I by A I epsilon I. So, these are the relations which we are going to use for this case. So, let us think of a 3 zone enclosure like this, where this is A1 maintained at a temperature T1 with an emissivity equal to epsilon 1. This is A2 maintained at a temperature T2 epsilon 2 and A3 T3 epsilon 3. I would like to find out what is the net radiative heat exchange between the two. So, the first thing that I would do is for 1, my potential is going to be EB1, which is inside the surface, but it is a black body radiative potential. So, it is a real surface, it is not a black body. So, its potential over here is going to be J1, here it is going to be J2, sorry J3, and here it is going to be J2. So, this is going to be my J1. On the other hand, over here I have this as EB2, which is this surface, it is connected to J2. In here I have EB3 with the radiative potential being J3. So, these are the 3 points or the 6 points that I have done. For each of the surface, the potential, if it is a black body, the radiosity, since it is not a black body, it is the radiative amount of radiation energy which is coming out of the surface as observed by an observer standing outside of the surface. Similarly, EB2, J2, EB3 and J3. These are connected by radiation, this resistance, which is this. So, what this resistance would be? This R1 would simply be equal to 1 minus epsilon 1 by A1 epsilon 1. This one and these two are R2, which is 1 minus epsilon 2 by A2 epsilon 2, and this is R3, which is 1 minus epsilon 3 by A3 R3. So, that is straightforward from our previous discussion. Now, this is now going to interact with 2 as well as it is going to interact with 1. These two are, this is the potential of 1 which is going to interact with 2 and it is also interact with 3. So, let us say it is interacting with 3 and of course, there is a resistance in here and J1 is interacting with J2. So, there would be resistance in here as well. So, what is the formula for interaction between J1 and J2? It is R1 to 2. So, it should be 1 by A1 F1 to 2. Okay. So, the resistance R12 would simply be equal to 1 by A1 F12. You can see clearly that it can also be equal to A2 F21 because of the reciprocity relation. So, whether it is R12 is expressed as 1 by A1 F12 or 1 by A2 F21, they mean the same thing, where F12 is the view factor of 2 from 1. In this case, this resistance is going to be R13, which would be only be equal to 1 by A1 F13, and this can, as I said, this can also be written as A3 F31. The one thing that is remaining in this to complete this circuit is between J3 and J2. So, what is in between J3 and J2? There must be some resistances in here as well, whereas where this R1 R2 to 3 or rather this R3 can be expressed as 1 minus the R23, this is between 2 and 3, R23 can be expressed as 1 by A2 F23. So, the connection between J2 and J3, the resistance R12, R13, R23 would simply be equal to 1 by A2 F23, or it can also be written as 1 by A3 F32 using the reciprocity relation. So, this essentially takes into account all the entire circuit, and because of the difference in values between EB1 and J1, EB3 and J3, EB2 and J2, some amount of heat is entering over here, which I call it as Q1, some is entering, which we call it as Q2, and some is entering over here, which is Q3. Now, the potential difference between EB1 and J1 arises due to the non-black nature of the body. Had this been a black body, EB1 would simply be equal to J1, and therefore, Q1 would be equal to 0. In the most general case, we do not assume that the body from where radiation is coming or the radiation is taking place is not a black body. So, there is a difference between the black body emissive power and the radiosity. So, a current, that is an equivalent heat, must flow from EB1 or J1, EB1 to J1 or J1 to EB1. So, Q1 can be positive or negative depending on whether J1 is less than EB1 or J1 is more than EB1. Another point which I would like you to remember is that the value of J1 is affected by the presence of other surfaces emitting radiation. So, whatever is the value of J1 is going to be dependent on whatever radiation it receives from the other surfaces. So, 1, 2 and 3, these three surfaces are therefore connected. Any change in the value of Q3 or Q2 would affect the value of J1 as well. So, this is the network method for 3 zone enclosures, and you would be able to find out what is the current at each of these nodes, what is the amount of heat that is to be supplied or to be extracted from node 1. The node 1 is surface 1 from this surface to maintain its temperature at a constant value. So, that is extremely important, and we will solve a number of problems on these, but let us think of a surface which is perfectly insulated. So, if one of these surfaces is perfectly insulated, that is known as the re-radiating surface, and a simplification can be made for the case of a re-radiating surface. So, in many engineering applications, a zone can be thermally insulated, and in such a case, the net radiative heat flux in that particular zone is 0, and such a surface is called a re-radiating surface. So, let us say this is a re-radiating surface, and in a re-radiating surface, obviously, the value of Q3 is equal to 0. Whatever it gets, it radiates the same amount. So, you have A1 T1 epsilon 1, A2 T2 epsilon 2, but this surface 3. So, this is 1, 2 and 3, surface 3 is a re-radiating surface. So, how would the circuit look like in that case? So, you have EB1, you have J1, this is J2, this is EB2. Over here, however, J3 is equal to EB3 because it is a re-radiating surface. So, if it is a re-radiating surface, then there is no flow of heat through this surface, and therefore, in such a case J3 is equal to EB3. Let us complete the circuit over here. So, I have a resistance which is 1 minus epsilon 1 by A1 epsilon 1. This is R2 is 1 minus epsilon 2 by A2 epsilon 2. So, in this case R1 to 3 should be equal to 1 by A1 F 1 3. this is R 2 3 would be 1 by A 2 F 2 3 and R 1 2 would be 1 by A 1 F 1 2. So, for this re-radiating surface, since Q is 0, there is no heat that is to be extracted or to be supplied in for a re-radiating surface. So, it is perfectly insulated, let us say, in which case since Q is equal to 0, E B 3 is equal to J 3. Okay. So, for a perfectly insulated surface is a close approximation to a re-radiating surface and Q would be equal to 0. So, E B 3 is equal to J 3. So, if I now consider between E B 1 and E B 2, if I am trying to find out what is the value of the heat to be supplied to Q 1, the same heat, in order to maintain thermal equilibrium, the same heat will have to be extracted from 2. So, if this is Q 1 and you have Q 2 in here, so Q 1 must be equal to Q 2 and this is simply going to be E B 1 minus E B 2 by the effective resistance between this and this. So, what is the effective resistance between these 2 points? This resistance R 1 and R 2 are going to be in series and the equivalent resistance of these 3, where these 2 are in series and which this resistance is in parallel with the sum of these 2. The equivalent resistance between E B 1 and E B 2 can be substituted and this would simply be where the effective resistance R, this effective resistance R would simply be equal to R 1 plus R 2. So, these 2 are in series and the equivalent of this, which is in series with R 1 and R 2, can simply be written as 1 by R 1 2 plus 1 by R 1 3 plus R 2 3 to the power minus 1. So, this is the equivalent resistance of these 3 of this entire resistive network, and when you take it further, this R would simply be 1 minus epsilon 1 by A 1 epsilon 1 plus R 1 2 is 1 by R 1 2 is 1 by F 1 1 by F 1 2. So, it is A 1 F 1 2 plus So, we have covered a number of interesting important observations in this class. Starting with the concept of radiosity and the concept of surface resistance to radiation, we went ahead and we found out what is the resistance to heat transfer between 2 surfaces, which we found to be equal to 1 by A 1 F 1 2 or 1 by A I F I j. Through the use of this surface resistance to radiation and the resistance to radiation between surfaces, which are functions of the view factor, I could create a circuit the same way we have done it in electrical technology, so to say. So, a 3-zone enclosure forming by 3 surfaces would have 6 resistances, 3 resistances each for each of these surfaces. So, 1 minus epsilon 1 by A 1 epsilon 1, 1 minus epsilon 2 by A 2 epsilon 2 and so on would form the surface resistance to radiation for these 3 surfaces. Each of these surfaces will have will interact with the other 2 surfaces, and the resistance in that case would simply be equal to 1 by F 1 2 or 1 by A I F I j. So, so the circuit which we have developed, then on one side I have EB1 surface resistance to radiation J1, EB2 surface resistance to radiation J2, similarly for EB3. So, I have the 3 nodes of a triangle where the potentials are J1, J2 and J3. J1, J2, J3 are connected by 1 by A1 F12, 1 by A2 F23 and 1 by A1 F13. That completes the circuit. So, I should be able to find out what is the net heat which is entering 1, which is entering through 2 and which is entering through 3. In order to maintain the thermal equilibrium, the algebraic sum of Q1, Q2 and Q3 must be equal to 0. We took it one step further, we defined what is a radiating surface, where it emits whatever it gets. So, it is a perfectly insulated surface is an example of a radiating surface. And I have shown you how for a radiating surface a 3-zone enclosure circuit diagram can be drawn, where there is going to be 2 surface resistances in series and the third resistance, which when you convert it, it gives you a simple expression for the net heat flow between these 2 surfaces. So, we are going to do a number of problems on this to clarify any doubts that you may have, and these are very interesting applications, real applications in furnace calculations. So, we will take those up in the next 2 classes.